Welcome everyone. I want to talk today a bit about quantum chip testing for the quantum utility era. And you might wonder why I want to talk about that. So there's two things I want to talk about. So the first thing, when I want to talk about quantum chip testing, is talking a bit about the quantum value chain. Because right now we're looking at this very often from a very bottom-up way. And I think by looking at the semicon value chain, we can really take some inspiration on how we think the market will evolve. And after that, I'll talk about the quantum chip testing as a key bottleneck in the development of useful quantum computation. For one reason, because I think this is one of the most important things that's limiting us, but the other is also that it's very selfish, this is what we are working on. So without further ado, quantum computing is becoming a reality. We wouldn't be here if it was not the case. And what I've done here is just highlight some of the most recent developments, highlights of all the years. Every year we picked one. Also want to highlight a few of the European aspects that are not so often talked about here. So for instance, we had the Quantum Inspire, Europe's first quantum computer, Quantware, the world's first quantum chip provider, and Europe's full stack quantum unicorn that has their own foundry these days. And of course this year, IBM has been dominating the news cycle. But what is really needed to create a quantum advantage? Now, I've created this visual here because it's sufficiently correct that a physicist will not instantly scream at me, but it's also something you can really put things in perspective. So on the x-axis, we have the number of qubits, and on the y-axis, the error rates. And I think one thing to look at a lot is the blue area. This is the area of everything that you could effectively simulate on a laptop or a moderately sized supercomputer. It's a pretty hard cutoff, after which you get into the area where you can't compute. And the yellow area is also known as the NISQ area. This is the unknown, where we might hope to find something useful, but we can't convincingly demonstrate that this is possible. And of course, on the top right, the promise of the future, fault-tolerant quantum computing. What's also interesting to look at is what's the current state of the art. This is all based on published data. One of the most important data points that's not there yet is, of course, IBM's announcement of a 1,000-qubit device that was announced today. But I think what you can really see is that we're now really entering this NISQ era where we can hope to find some form of quantum utility. And that's really important because fault tolerance will take us a time. But what's most important is that in the near future, we will actually move this top right. And I hinted at this before, but this task cannot be achieved by scientific breakthroughs alone. So what should we do? And it's really a different way of thinking. So what I'll do is I'll take a look at the semiconductor value chain for some inspiration. And what's a value chain? A value chain is effectively a process that identifies each step in which value is added to what's relevant to the end user. It has to do with applications at the end. If there's no end user, there's no value. And if we're looking at the state of the semicon value chain, there's a few things that are really different from quantum, but also it's a mature market, but we also have clear niches. And what's interesting is to look at what's common between all these niches. For instance, if you take ASML as a highlight, that's really niches exist around tackling key problems. And each of these steps in the value chain has their own vertical behind it. So there's really an industry between each of these pillars, and they're really different in a way. And the reason why I'm looking at this is because I expect the quantum market to evolve to something very similar. Sufficiently different that we can't tell how it will look, but sufficiently similar that we can take lessons. So looking at that, where are we today? Well, we're just leaving what I like to call the R&D phase. The R&D phase was the 2010s to 2020. You have an R&D market. It's largely dominated by academia and corporate research groups. There's no specialization yet. There's very few suppliers. And that also implies that the only viable strategy at that point in time is to be a full stack player. You had to do everything yourselves. And also because it's R&D, there's still limited end user value. And I'd like to highlight one company in particular because in some sense they've paved the way. Rigetti really was the first quantum computing startup that did full stack and was forced to do everything in-house. And I think that now the question is then, if we're talking about a value chain, And I'm saying that this value chain will emerge around hard problems. What are these problems? And I think there is 3 main problems that we need to tackle where value can be added. The first one is the quantum applications problem. I'm a physicist who likes to be in the lab and build things, so I'm not suited to deal with that. But this is a very big topic, and this is where it's closest to the end user value. The next one is system integration. Can you actually build a system that integrates all these components and is powerful enough that you can do it? And the third one would be in the quantum chip development. That's the one I'll be focusing on the rest of the talk as well. So going back to how I anticipate this value chain to evolve. So what I expect in the NISQ era, which is effectively 2020 until 2035. We'll see when we really hit the next phase. But what we're seeing today is we're seeing a vibrant, emerging quantum industry. And it's largely dominated by big tech and venture capital. But what's really unique is that because of its size, specialization is becoming viable. But you need to be very careful, what do you want to specialize in? What is something that we believe to be valuable on the long term? Now, when you can specialize, that also means that buy or build discussions become prevalent. Because if you don't have to do everything anymore, what really is your core business? And of course, this is the big thing we're all talking about, quantum utility. Is there a way we can already do something that's useful? And here there's a particular company I'd like to highlight as a sort of case study, is Q-Control, because they started already in this R&D phase. They were really ahead of the curve in that sense. And they tackled a problem that's really specialized, namely getting these qubits tuned up. And I think their recent announcement with a collaboration with IBM is really unique, but it also really emphasizes that if you solve a hard problem that is not the core business, you can carve out a very valuable place in this value chain that will also stabilize. So what's beyond? Well, in the end, and here I won't put any logos or any names or any positions, simply because we don't know yet how this market will evolve. But as we have fault-tolerant quantum computing, we expect to deliver on the full potential promise of quantum computing. We'll have a mature quantum industry dominated by industrial players where you have this value chain with these clear niches, but these are shaped today. And also not important, there's significant end user value. We're no longer relying on government and VC-backed funds to fund the R&D efforts required. So moving on to the second part of my talk. I mentioned I wanted to talk about a particular niche here, namely the development of quantum chips, and specifically quantum chip testing. So as a framework for this, I'm using a recent publication we made together with IMEC, a well-known entity from Europe in the semicon world. And basically we looked at, okay, so what would be required to produce these quantum devices at scale? And we identified basically 2 parts. One is we need to have foundry-compatible processes, and the other is we need to have novel test infrastructures. And the interesting thing, which is really surprising if you think about it, is that if you want to make quantum chips, and this is, for instance, an image of a superconducting device, then this is already possible with today's technology. So this is a publication that IMEC made about the subject. They've also shown the same with spin qubits. There's also similar publications by Intel on spin qubits. But it's not a secret that you can actually make superconducting devices with foundry-compatible processes. So the technology is there. So if the technology is there, what's then really limiting us? And then we really get to the novel test infrastructure. And for that, I need to go a little bit more technical. So what do you need to do to build better chips? You need to establish a fast feedback cycle in which you're constantly iterating on your design, your fabrication, then you're measuring it. And interesting about quantum, you can do this both on the device level, that you're measuring physical properties like the coherence times, how close are you to your target parameters, or at the quantum algorithm level, where you look at what are my gate fidelities, or even more high-level metrics like quantum volume. These are really tied to your end application. But to do this, What can you actually do? So what do we need to know? What's the information that's relevant to us? And the simplest thing we can do is material properties. And this is something we're actually really good at classically. This can be measured at room temperature. There's established protocols, but it doesn't really get you what you need. To do that, you need to go further. You want to have your quantum physics-based properties and your quantum information properties. And this is typically hard and at cryogenic temperatures. So that brings me to the next part. Me saying, why is quantum chip testing hard is the same thing as me asking, why is quantum chip testing valuable? So it all boils down to these quantum operating conditions. We need to be able to observe these quantum mechanical effects to see how coherent are they, how long do they last. And the first part about these operating conditions is that you need to put it into a quantum environment. And for most qubit types, specifically solid-state qubits, this means that you go down to cryogenic temperatures, lots of shielding, and effectively very complex, expensive systems. Just to give you some ballpark figures, simply a cryostat, nothing in there, you're already close to $1 million without having a system that can do anything. Throw a few cables in there, single control line, $2,000 to $8,000. Every qubit needs 2 to 4 lines. You can do the math. You got a system that's cost multiple $1 million that cannot do anything yet. You haven't even started testing. And the next part is you need to have a physicist that typically is doing some semi-manual operation to tune up all these qubits before we can figure that out. So that's a big problem. And it's not an insurmountable one. It's an engineering challenge. It's not fundamental. But the way that we're typically dealing with this, and there's a few exceptions to this, but that at the 20 qubit scale, we're using an R&D system. It looks like this. This is the one that we have in our lab. We call it a lab because it's an R&D system. They're full stack quantum computing setups, and they double as a research system where we want to try out all our cool new stuff. It's a quantum computer. The first generation quantum computers that connect to the cloud look like this. And it's a test system. So this is also feeding into the hero device discussion that you may have heard of, where people really select the very best device they have to do that. And this is a problem. And Intel says it's a problem, so it must be true, right? So what can we do about this? Well, as I mentioned, it's not a fundamental problem, but it's a very tough engineering challenge. And it starts with acknowledging that if you have different applications, you have different requirements. It sounds kind of obvious when I'm mentioning it like this, but first thing is quantum computing research. What do you need? Well, first and foremost, you need to be flexible. If you have a new idea, you want to be able to use it. And this flexibility is precisely what allowed this first generation, essentially up to the 2020, to be able to be done in this research system. You can actually make a quantum computer, you can run your algorithms, you can make your Nature publication, but you cannot scale. Because for quantum computing, scalability becomes important. Stability becomes important. Having a well-defined, constrained API becomes important. Your abstraction layer becomes important. And this is what you see really the quantum big tech doing. They've established these very well-defined APIs that also allow us to build application layers on top of it, for instance. But what's very much missing is always in discussions about the quantum computing. That's our core and focal point. We still need R&D because we still want to be able to develop new qubit modalities or new designs. It's not obsolete, you still need that, but it's something different. And what I want to also put in there is that quantum chip testing is something different. Because you can do that in a quantum computer, and you can do it in a research system, but you cannot hit your fast feedback cycle. Because what you need is you need a system that's turnkey. You don't want someone with a PhD sit in there, spend weeks measuring and keeping the system operational. And you also don't want to spend the same amount of money that you need to build a full quantum computer. So if you make an integrated solution, you can actually take some trade-offs. So what you see here is like the layering of a full-stack quantum computer. You see the designs of one of the systems that we're currently building. And I just want to highlight a few of the innovations that you can do that when I highlight them, they sound kind of obvious. But the point is not whether they're obvious or not, but that it's something different. So, for instance, if you include a switching matrix because you realize that, hey, maybe I can do more qubits per thermal cycle, that would be good because it makes the system cheaper. And hey, maybe we can also automate this tune-up. And there's a cool video we made. This is recorded in our lab on live qubits. And what this looks like, I'm not expecting you to understand what you're looking at, but I want to get you some feeling of what a human would normally be doing. So what you're looking at is a sped up video of effectively a calibration graph, where every node corresponds to a different experiment. And on the right, you're seeing data come in real time. This is sped up. This takes 8 minutes per qubit, which is rather fast. And you can also see like all the artifacts and other things. But this is a thing that normally a physicist would have to do by hand. And this particular device, we get this working reliably on all the different qubits of this device. And that makes us very happy because in these kind of things, it's really the devil's in the details. Getting the top thing to work once, that's easy, but making it always work, that's the challenging part. So, now we get to the end. What are the takeaways that I want to share with you? So, I spoke a bit about the quantum value chain. What should we do there? I think it's very useful to look at semicon and realize that it's sufficiently similar that we can learn something, yet also sufficiently different that it's not a one-to-one mapping. But if you understand what drives that, we can learn something from it. And in this case, I think the fact that the value chain contains niches that are valuable, that's obvious. But the lesson is they form around challenging problems. That makes it that it becomes a suitable vertical. The other one, about quantum chip testing, well, we need more and better qubits, so it's kind of important. And surprisingly, in quantum chip testing is the bottleneck for developing better quantum chips. And that's different than in the semiconductor market, where the testing space is only 20% of the market, and 80% is for the fabrication tooling. I expect that this will be the reverse in the quantum market. And to address this bottleneck, we really need to start to think about integrated solutions that are turnkey and solve this problem on a high level. There's also some references here for further reading. These are 2 papers that we've published, one together with different companies from the Dutch ecosystem in EPG quantum technologies, and the other one together with IMEC in the SPI advanced lithography. Feel free to look them up or find me after the talk. For now, I have time for any questions.